A high voltage gain switched capacitor-based boost DC-DC converter. Abstract. This paper, going to propose a high voltage gain switched capacitor-based boost DC to DC. For reducing the stress of the diodes, MOSFETs, and conduction loss on the switches, uses small duty cycle. This converter has an advantage of high voltage gain and a simple structure. The converter can make 300 V output from a 50 V input with a duty cycle of 17%. Matlab/SIMULINK R2017a is used for simulation works. From the analysis, a voltage gain of 6 is obtained at 360 W output. Based on the simulation results, analysis is done. Arduino microcontroller is employed to produce the switching pulses for the control circuit. To verify the performance and operating principle, output voltage of 300 V and input voltage of 50 V with output power of 360 W prototype is constructed and the results are validated. Keywords: boost converter, dual switch, switched capacitor, non-isolated DC, DC converter, high voltage gain continuous conduction mode, CCM. Introduction. DC-DC converter with high gain has increasing demands in recent days. High step-up DC-DC converter is a class of converters which can boost a low voltage to a relatively high voltage. As we known, the output voltage of fuel cell stacks, single PV module, battery sources, or the supercapacitors is relatively low. It should be boosted to a high voltage to feed the AC grid or other applications like uninterruptible power supplies, new energy vehicles, and so on. Lots of research works have been done to provide a high step up without an extremely high duty ratio. The isolated converters can boost the voltage ratio by increasing the turns ratio of the high frequency transformer. However, the leakage inductor should be handled carefully, otherwise, it will cause voltage spike across the power switches or diodes. Moreover, isolated DC-DC converters have the shortages in system volume and efficiency due to multistage DC-AC-DC conversion. FL Toffoli 2 introduced a step-up DC-DC topologies that feature high efficiency, reduced stress, low cost, simplicity, and robustness. WLI 3 introduced a power system for the downstream DC-AC grid-connected inverter which require a DC-DC converter to step up the low voltage of fuel cell or PV to a high bus voltage. YP Sawakati 4 introduced a new DC-DC converter, derived from the traditional Y-source network. The proposed circuit inherits all the advantages of the Y-source, including very high boost capability and .x ability to choose multiple circuit parameters to tune the gain. Minkai Nguyen, Truong De Duong, and Youngcheol Lim 1 proposes boost DC-DC converter which employs the use of switched capacitor. It consists of two switches S1, S2, 3 diodes D0, D1, and D2 and 1 inductor L and 3 capacitors C0, C1 and C2. Vg is the input voltage and output voltage is denoted as V0. Figure 1 shows a typical arrangement of the converter. The circuit is analyzed on continuous conduction mode, carries some assumptions such as all devices are ideal and lossless, the capacitor values are large, the current owing through the inductor decrease or increase linearly. Fig 1. Switched capacitor-based converter. In mode 1, switch S1, S2 are turned on. At the same time diode D0 will conduct and diodes D1, D2, and D3, will not conduct. The inductor L gets charged and the capacitor C1, C2 will discharges its energy. D*T is the time duration taken for this mode, where T and D shows its switching period and duty cycle of the converter. Both the switches are turned O in mode 2. The diodes D1 and D2 will conduct and diode D0 will not conduct. The time duration for this mode is D*1D. During this mode the energy stored in the inductor L will discharges, and the energy will stored in capacitors C1 and C2. In order to improve the voltage gain of the circuit pointed above, modified the circuit by adding a switched inductor circuit in the input side. By adding switched inductor circuit in the input, it is observed that the gain can improve to 6. There is no any difference in designing aspects. 2. Proposed converter. Proposed high voltage gain switched capacitor-based boost DC converter is shown in figure 2. It consists couple of power switches, S1 and S2, 2 inductors, L1 and L2, 3 capacitors, C0, C2, 7 power diodes, D0, D6, and a resistive load, R. Fig. 2. Proposed converter. The following assumptions are taken consideration while designing the converter. 1. All components are taken as ideal and lossless. 2. To maintain the constant capacitor voltage, capacitance of the capacitors are made high, and 3. The current in the inductor will increases or decreases linearly. The circuit diagram of the high voltage gain switched capacitor-based boost DC converter in continuous conduction mode is shown in Figure 2. 3. Operating principles. The working of the circuit can be explained by two modes of operation. Figure 3a and 3b shows the operating modes of high voltage gain switched capacitor-based boost DC converter in continuous conduction mode. Switches S1 and S2 will turned on in mode 1 and off in mode 2. Fig. 3. Operating modes of the high gain switched capacitor-based boost DC converter, A, mode 1, B, mode 2. Mode 1, Fig. 3a, shows the circuit diagram in mode 1. Switch S1 and S2 are turned on in this mode. The switches allows a path to charge the inductor L1 and L2 and discharge the capacitors C1 and C2. The diodes D0, D4, and D5 are forward biased, and the diodes D1, D2, and D3 is in block state. D*T is the time duration taken for this mode, where T and D shows its switching period and duty cycle of the converter. By applying KVL in Fig. 3a, the following formula is derived. Mode 2, Figure 3b, shows the operating mode 2. S1 and S2 switches are turned off at this mode. The diodes D1, D2, D3, and D6 will conduct, and the diodes D0, D4 and D5 are blocked the current flow. 1D*T is the time duration taken for this mode. During this mode, the inductor L1 and L2 are discharged through the diodes D1, D2, D3, and D6 while capacitors C1 and C2 are charged through the same path, and the following formula is derived. Substitute equation 1 to equation 4, after applying volt balance law to the inductor gives the following equation. Proposed converter's output voltage gain in the CCM can be obtained by substituting equation 5 in equation 2, and is shown in equation 6. The output current of the proposed converter is equal to the average current of the diode D0. By applying KCL in node A of Figure 2, average inductor current of the converter is as follows. 7, 12 in 0 thurial plus equals. 4 design considerations. A voltage and current stress on the switches. By analyzing the operating mode, the input current is equal to the switch current, IS, in mode 1, and is equal to the inductor current in mode 2, following equation shows the average input current. The peak current of the switches S1 and S2 can find out by substituting equation 7 in 8, and is as follows. B voltage and current stresses on the diode D0. The peak current of the diode D0 is calculated based on the operation in mode 1 shown in Figure 3a, is as follows. C. Inductor selection. Using equation 1, we can calculate the peak-to-peak inductor current. By considering the ripple current of the inductor. IL equals RI%IL. The value of the inductor should be as follows. D. Capacitor selection. The capacitor voltage ripple is considered while designing the capacitor value. By analyzing the current flow, the switch S1's peak current and current flow in capacitor C1 in mode 1 seems to be same. The peak current of the diode D0 is equal to the current. Ow in the capacitor C2, therefore the equations be like. The capacitances for the capacitor C1 and C2 of the converter is as follows. By considering capacitor peak-to-peak voltage ripple, the capacitor voltage is restricted in amount by RV%. The output current in mode 2 is equal to the current. Ow in output capacitor C0 as shown in Figure 3b. B. The C0 capacitance is designed so as to reduce the ripple on the output voltage. V. Simulation results. The simulation parameters of high voltage gain switched capacitor-based boost DC-DC converter is given in Table 1. An input voltage VEN of 50 V gives an output voltage VO of 300 V for an output power PO of 360 W. The switches are MOSFET/diode with constant switching frequency of 50 kHz. The duty cycle of switches is taken as D equals 0.17. The high voltage gain switched capacitor-based boost DC-DC converter is simulated in Matlab/SIMULINK by choosing the parameters listed in Table 1, and the SIMULINK model is shown in Figure 4. The simulation results of the high voltage gain switched capacitor-based boost DC converter is shown in the following curves. The switching frequency is 50 kHz. The gate pulse of main power device has .xed duty cycle of 17%. It can be seen from the Figure 5a, and Figure 5b, and 5c, that the output current is 1.2A, the output voltage V0 is about 300 V and output power is 360 W. This allows high voltage gain of low stress converter. The output voltage has a ripple of 0.2% as shown in Figs 5f, and 5g. The voltage of the capacitor C1 and C2 is boosted to 129 V. Figure 5a, output current, B, output voltage, C, output power, D, voltage stress S1, E, voltage stress S2, F, voltage across C0, G, voltage across C1, H, voltage across C2. Figure 6a, voltage across D0, B, voltage across D1, C, voltage across D2, D, voltage across D3, E, voltage across D4, F, voltage across D5, G, voltage across D6. 6. Analysis. The analysis of high voltage gain switched capacitor-based boost DC converter is carried out by considering parameters like voltage gain, efficiency and duty cycle, etc. Fig.7. Voltage gain vs duty cycle. A typical curve for the voltage gain vs duty cycle is shown in Gur 7. For a duty cycle of 17%, the efficiency is 97%. A typical curve for the efficiency vs duty cycle is shown in Gur 8. For a duty cycle of 17%, the efficiency is 97%. Thus the efficiency of a switched capacitor DC-DC converter decreases with increase in the duty ratio. The comparison of modified converter with conventional Scdc converter is given in Table 2. A prototype of high voltage gain switched capacitor-based boost DC-DC converter with input voltage of 50 V is implemented. The top view of the experimental setup is shown in Figure 9. It consists of control circuit, driver circuit, and power circuit. Control circuit is composed of Arduino microcontroller and its power supply. The control pulses for MOSFET switches are generated using Arduino microcontroller. The pulses from microcontroller are amplified by driver circuit. It also provides isolation between control and power circuit. 7. Conclusion. High voltage gain switched capacitor-based boost DC-DC converter boost input voltage to a very high value. Moreover, it has low switch voltage stress, and conduction loss on the power switches. The switches and diodes have relatively low voltage stresses, and hence the switching and conduction losses are reduced. It achieves an improved overall efficiency. The input and output voltages of the converter verify the high boost voltage gain. The converter has an efficiency of 97% and voltage gain of 6. A duty ratio of up to 0.17 is suitable for this converter so as to keep the voltage stress across the switches and diodes to a safe limit. The converter can be used for applications with high output voltage and can handle small output current. Moreover, it can be used as LED driver and can be also used in solar system. High voltage gain switched capacitor-based boost DC-DC converter can be also introduced in DC motor drives, electric automobiles and marine hoists. Moreover, it is used in high voltage low current applications such as accelerating purpose in cathode ray tube.